Hello, my name is Kumar Shaswat, and today I will be explaining you Capsule Network or CapsNet. What we will cover. We will discuss the drawbacks in CNN which led to development of Capsule Network and what are the few more requirements that we want from the Capsule Network to cover. Let's oversimplify CNN for the revision. CNN does is detects edges and color gradients and defines it as a feature. This first learning to detect edges and color gradients is actually the lowest level of features. Now, when we go deeper into the layers, these features combine into more complex features, and then in the third layer, very dense, finally the dense layers will combine very high level features and give a classification prediction. Now, what is the CNN's drawback? CNN has a drawback that in these both pictures, CNN will say it is a face. Why? CNN will detect a lip. In both pictures, those lips are present. CNN will detect if there is a nose. There, in both pictures, the nose is present. Similarly with the right eye and the left eye. So it doesn't matter where these features are present. If they're present in the photo, it will say it is a face. Their spatial position is not recognized by CNN. To solve this solution, to get a solution from this, CNN applies a temporary solution which takes a lot of data out of your equation. That is right. CNN's band-aid is max pooling. It reduces the spatial size of the data to give a field of view or the bigger picture, you can say. The developer or the one who developed with his team, Hinton, said that max pooling operation used in convolutional neural network is a big mistake, and the fact that it works so well is a disaster. Now let's continue. Now, what we require from our CapsNet. The requirement is that all these pictures of Liberty, Statue of Liberty, for us are the same, but CNN, until and unless we have all these features into the CNN, it will perceive these features as different. So we need to incorporate the pose or the 3D orientation of the model and positioning of the different features into our network or model. So what did Hinton say? Hinton argued that the brain do the opposite of the rendering, that is inverse graphics. From visual information received by the eye, it deconstructs a hierarchical representation of the world around us and try to match it with already learned patterns and relationships stored in the brain. Now, let's simplify this as enough. What we do when we look at the object, we have previous experience of the same object, so we deconstruct the image into a 3D representation of it. So to getting a clear picture, let's see this with the picture. Now at the first set of images, on the above part there is a lion, below there is a dinosaur. We can tell the difference. In the second pictures are of the same model or soldier. And the third picture is a plane with a propeller on its head, and the second below that the propeller is not present. We can say the differences in between them. We want our model to do the same. So let's introduce CapsNet or Capsule Network. What is a capsule? Capsule is a group of neurons whose outputs represent different properties of the same entity. Now, let's take an example of a face, since we are considering that, and we discuss drawbacks in the face also. So if a nose is a feature, so its position in the face and how it is placed on the face is the property of the entity, that is the nose. And the property is where the position is on the face and what is the proportion of the nose. Capsule network. Now the idea is to add these capsules to a CNN to reuse the output from the several of those capsules that agree with each other to give a better classification of a model with spatial representation. CapsNet architecture. This is an overview picture. We'll discuss this in detail in the next slides. Now, CapsNet architecture consisted of two parts, encoder and decoder. In encoder, we did convolution layer, then we used capsule layer, then we did digit caps layer. In the decoder part, we reconstruct the image from the digital caps output to give the image with the same accuracy that we started with. So we already know what a convolutional layer is. The input we take is 28 into 28, that is in CapsNet. The number of parameter is 20,992. Kernel size is 256. Size of the kernels, that is filters, is 9 into 9 into 1. Now 9 into 9 into 1. Why? Because the input we are taking is MNIST dataset. So we don't have that channels of colors. So it is almost a two-dimensional picture, right? 28 into 28 into the channel of colors is 1. So filter size is 9 into 9 into 1. Output is 20 into 20 into 256 as a tensor. And we are taking stride as 1 in the CNN. Now, primary caps layer. There are 32 capsules that were presented by Hinton in his CapsNet. These capsules each applies these all things, strides and number of parameters we'll understand in the next few slides. This is just a representation of the number that we have. Now, on the left side of the slide, you can see there is a set of 256 outputs that we got from the convolutional layer. Now, from this, we'll take 9 into 9 matrices from the filter and get one output into a 6 by 6 matrix. Now, this 6 by 6 matrix has 8 layers, and one, as we go towards the right, we can see that 256 layer gives one output of 6 by 6 that has a repetition or channels of 8. Now this each of this channel of 1 by 1, the capsule is already marked into the image, if you can see. So how does the capsule net works? Let's take an example of the nose as we have taken it before. U3 is the vector, the nose capsule that in existence and the pose of the nose. We add the weight matrix that encodes the spatial relationship between nose and the face. Then we get U3 cap, that is matrix multiplied output of a lower level nose capsule. We add the scalar weight determination by routing algorithm. We'll discuss the routing algorithm in the further slides. We don't add a slide or add any bias in this layer, that is primary caps. We squash the output into a linear vector that has a scalar, and that is almost a scalar entity with a direction. The output of the phase capsule that encodes the existence and the pose of the network. Now, towards the right, we have the equation, how we are squashing it. This is the output. This is how the output of the vector or the vectors are squashed into a scalar with a direction. Digital caps. Digit cap layer contains 6 by 6 into 8 into 32. That is the output of the primary caps layer. 1152 tensors. Each 10-digit capsule for each digit. So every 1152 has 10 digits. Okay. The weight of each tensor is 8 into 16. Now, we take two type of coefficients here. One, coefficients that are coming from the CNN, that is represented here as B. Now, C is represented as the coefficients we are coming from the primary caps layer. I'm sorry about that. Output is in 16 into 10 matrix. Now on the right side, if you see, there is a representation of one of these matrices output. Okay, the white part is the most positive value of those stacked values, right? So lighter the color, the more positive; darker the color, the more negative. CAPSNet loss function is represented here. We are taking L1, L2 norm to suggest, then the TCs, calculated the correct digit caps, calculate for the incorrect digit caps, and everything loss function is there. Now fully connected layers, these are triplets. They do exactly the same, they take the same input, they give the same output. Okay, the input is 16 into 10, that is the digit caps that we got, and then output is to 512. The number of parameter considered is multiplied, and you will get the exact amount of it. So these reconstruct the image from digit caps output. So in summary, steps involved in a CAPSNet are input, you do the convolutions, then you do the value, then you go to primary caps, then you squash the value, then routing by agreement is done, then you get digit caps. And then if you want to reconstruct the image, you will use the decoder. Now routing by agreement. Lower level capsule will send its input to the higher level capsule that agrees with its input. Now what does this mean? Through this representation or this figure, we'll understand that. Now, J capsule and K capsule are two different features with the same input from the smaller feature or smaller cap that is marked in blue. Some lower level capsule will agree to the bigger level capsule, then only the bigger level capsule will agree that such a presentation or classification exists. These are the references that I got through to discuss this paper and presentation. Thank you.